Artificial intelligence has been treated as a software problem, but housing the next generation of these models requires a massive commitment to physical infrastructure. Global data center capacity is expanding at a 14% annual rate, on track to reach 200 gigawatts by 2030. The drivers are shifting. By 2027, inference workloads, the daily operation of running AI models, will overtake the compute cycles used for training. Training requires periodic, localized bursts of energy. Inference for billions of users demands a relentless, continuous power draw on a global scale. Existing electrical grids are struggling to meet this baseline. In primary data center markets, the wait time for a grid connection now exceeds 4 years. Air-cooled architectures built for intermittent training spikes are unsuited for the continuous thermal load of a 200-gigawatt inference-heavy future. The shift toward inference is driven by a change in how AI models process information. Yann LeCun argues that today's autoregressive large language models lack a true understanding of the physical world. Current text-based models guess the next word in a discrete sequence. World models process a continuous, high-dimensional stream of sensor data. A single pair of smart glasses feeds 2 megabytes of visual data every second, requiring significantly more sustained compute power. Running these continuous sensor streams at a planetary scale forces individual server racks to operate at power densities far beyond historical standards. This move from text to continuous reality creates a mechanical problem. It reaches the physical cooling limits of existing data center infrastructure. This 3D thermal map shows heat at 100 kilowatt rack densities, where forced air cooling fails. Nanogen requires a closed-loop fluid network pumping coolant to the chips, transferring heat to a coolant distribution unit, like the Vertiv Liebert XDU 1350, to manage exchange with the primary water loop. To protect the microchannels, these units must include 50-micron filtration to prevent debris from causing blockages. Precise temperature regulation within the unit is necessary to prevent the thermal fluctuations that shorten the lifespan of high-end silicon. Ultimately, extracting maximum compute from a fixed power budget completely relies on the immense mechanical efficiency of megawatt-scale liquid cooling. Solving the intense heat problem suddenly exposes a massive secondary bottleneck hidden within the network fabric connecting those GPUs. Training and running these enormous models requires thousands of GPUs to constantly synchronize their work through collective operations like all-reduce. This grid illustrates tail latency. If a single data packet delays, the entire cluster stops. Current routing uses flow hashing, forcing entire data streams down single paths. This creates congested links that bottleneck the system, even while adjacent parallel paths remain completely empty. Adding more GPUs offers diminishing returns if the network protocol frequently leaves those processors idle. The Ultra Ethernet Consortium specification was designed specifically to address these networking inefficiencies in AI clusters. This shows packet spraying. Instead of a single path, it breaks the data flow, sending pieces across every available link simultaneously. Arriving out of sequence, Ultra Ethernet delivers these packets directly to memory the moment they arrive, completely removing the wait for resequencing. The specification also includes end-to-end telemetry. Switches monitor traffic levels and immediately signal congestion to prevent the data collisions that cause network crashes. Packet spraying and real-time telemetry allow the network to maintain high link utilization, ensuring the GPUs spend less time waiting for data. Every layer of this stack is interdependent. World models require inference. Inference requires high-density racks. Racks require liquid cooling. And massive clusters require high-utilization network fabrics. Building this will require $1.2 trillion in real estate development and an additional $2 trillion in technology fit-outs by 2030. The next phase of AI development is constrained by the physical and thermodynamic limits of hyperscale infrastructure.